to apply gradient descent algorithm, we need to make sure that the function is differentiable and it's convex. Okay, these are very important. Without that, the gradient descent algorithm will not work. So what is differentiable? Means it has a derivative for each point in its domain. Okay, so it cannot be a function at sudden break or discontinuity. Any step function will not work with having a cusp, right? Root over of mod x, or discontinuity like fx equal to 1 over x. This kind of functions will not work. You cannot have a discontinuity or step or a cusp or anything like that. So every point the function should have a derivative. Okay, so it has to be convex. Convex means on the function, the graph of the function, if you take any 2 points and you connect them with a line, the line must be above the function. That means should not cut the function line by any. So let's see. So if we take 2 points on this graph and then we kind of join them, that line is above the graph. So this is a convex function. Okay. But this one, where this is a function graph and you take any 2 points and we connect them with a green line, that line is cutting the function graph. So it's not a convex function. Okay, it's a non-convex function. So the function has to be convex and differentiable at every point to make sure that gradient descent algorithm can work. Okay, so now, so this is one more time. This graph we are getting from, for minimizing the sum of the squared errors, which is a quadratic function again. That's why this is a parabolic graph. So you have to understand that at this point where this is on the y-axis where x equal to 0, so the sum of the square, it's pretty high. And when we change the intercept little by little, we can see that the sum of the square is getting down and down. Now we have to understand one thing. If we go too far, so this side, that means the x is too high, again the sum of the square will grow. Okay, so because it's a quadratic function, so it will again grow if x is too high. Because that means it works in both positive and the negative direction. So one thing I want to tell you, that our job is to come down towards the direction of the steepest descent, but also we have to stop at the correct position, otherwise we'll kind of shoot over. Okay, so to explain it, so let's think about it, that we are coming downhill, and of course when we come downhill our speed increases. Okay, and if we see a steep slope, we'll probably run down, and then there is a chance that we may not be able to stop at this point, which is the, let's say, a road or something, and then we might go up a little bit higher, and then we kind of miss that minima. So this is a very important point, and we have to make sure that we can stop there and stop at the minima. So here, let's say we are standing at the top of the Mount Everest. We want to go down in the direction of the steepest slope, because the steepest slope also ensures that you go down fast. Okay, you converge to the minima fast. And at the same time, you have to make sure that you don't overshoot and go to the other direction. So because from the top of the Mount Everest, you can go any direction and find the steepest slope. There is a 360-degree panoramic view from the top. But when you are taking a particular path, you are calculating slope on that path. So in that way, at every point, you calculate the slope and find which one is the best slope or the steepest slope, and you go down that path and continue on that. Other paths you don't care. That's why when there is a multivariate the function is there, so we have to make sure that we take for an n-dimensional function, fx at a given point p is defined by del fp, which is a set of partial derivatives with respect to all the points, let's say all the directions of coming down from the Mount Everest, and then we choose the one with the highest gradient for descent. So this is a function f of x equal to half x squared plus y squared. So what we do, we find the first order derivative of the function, the multivariate function, two different parameters x and y. So we calculate del x with respect to x and y, and also we calculate del f del y with respect to x and y. So when we calculate with respect to x, the y will be considered as a constant. That means I'm not looking at the other direction or other path from coming down the Everest. It doesn't matter to me. So it's constant. I don't even think about the slope in that path. So when we solved it, we'll find x and 2y. Okay, these are the partial derivatives. And then at a point 10, 10, we find if x equal to 10, then y equal to 20. That means for a change in x for 10, the y is 20. So that means the slope is pretty high. So this is the way we calculate the gradient at a particular point using partial derivatives or multivariate function. This graph, we want to tell that this is a two-dimensional graph because we are only trying to, minimize the function with respect to the slope. That means we are trying to find out where the sum of the squared errors is minimum with respect to the intercept, not the slope. Okay, so if we consider both slope and intercept, it will not be a two-dimensional function anymore. It will be a three-dimensional function. Okay, so there will be both x, y, and z dimension, and let's say one is the intercept, other is slope, and this will be SSE, and so this will be a graph in a three-dimensional space. And with respect to that graph, we have to reduce the value or find the minima of that function, where there will be intercept, slope, and SSE, three different dimensions. Multivariate function, it's easy. Okay, we just take the first derivative at a selected point, and that's all. So that is the gradient at that point. But for a multivariate function, as I said, from the top of the Everest, you can have multiple different directions through which you can go down. And then if we consider each of these possibilities as a different variable, then it will actually give us different possible derivatives, right? So then it will create a vector of derivatives in each direction, in each different direction along for different variable axis. Okay, but at a particular point, we are just interested in one particular direction, because you cannot go down through multiple paths at the same time. So when we are going down a path or calculating derivative of a particular path, we do not consider the other paths or other variables. So we do the derivative, or we take the gradient with respect to one particular variable and forget the others, and so we consider them as constant. So because we are interested in slope only in one direction or one axis or one particular variable or feature, we do not need to consider the other directions, and we consider them as constant. And these derivatives are called partial derivatives. Okay, so gradient for an n-dimensional function will be, there will be n different partial derivatives with respect to those n different variables, and at a time one particular variable will be considered, and the rest n-1 will be considered constant. So this is the way we have come down to this vector, where del f of p at point P will be will have a vector of n different partial derivatives.